Okay, in our discussion of determinants, we're really going to have to do this dimension by dimension. So what I want to do is just start out with dimension 1 and talk about what a 1 by 1 determinant is. Remember that a 1 by 1 matrix is just a number, right? And the determinant, usually you put just 2 bars like that, should just be the number itself. Now this does have geometric meaning. If I look at R1 and put a vector in R1 like A, right? A really should be that vector like that. And the determinant should tell you the length of the vector, right? So it's going to have length. And then length should just be the absolute value of A, right? That's not the determinant. And it should also have direction. Every determinant we will see this semester has some geometric meaning, and it has a direction. Now the direction here is just right if A is positive and left if A is negative. So that's it for 1 by 1 determinants, but they actually have length and direction. Now let's look at 2 by 2 determinants. If I look at 2 by 2 determinants, so n equals 2, like that. Remember that a 2 by 2 matrix, we usually write something like that. So it has 2 columns. The determinant, we usually just write 2 bars like this. I mean, we can write the word determinant, but this is actually much more common in later courses. So if it's got brackets, it's the actual matrix. If it's got bars, it's the determinant. And somehow, some way, since this is 2-dimensional, it's not length, there should be an area, and it should involve some direction. And we'll talk about the direction after we do a calculation. Now, what is this supposed to be the area of? It's supposed to be the area of the parallelogram that's formed by the 2 columns. Let me do an example using probably about half the linear algebra you had in your algebra class. And what I want to do is find the determinant of the matrix 5, 2, 3, 7, like that. Now, what it's supposed to do, it's not going to be a length, it should be the area of a parallelogram. So let's draw the parallelogram first. And then we'll have to do some calculations. 5, 2 is over here somewhere, right? 3, 7 is up here somewhere. If I draw the 2 vectors, I'll draw that and that. And what we want is the area of the parallelogram formed by the 2 vectors, just like that. Now, how are we supposed to do that? Well, what we're going to do is to cut off this piece. This is actually what they do normally in a geometry class, right? And we paste that piece, if I had drawn it perfectly down here, this piece right here would fit in exactly right here. So instead of finding the area of the original parallelogram, I'm going to find the area of, okay, that one didn't work. I would like this new parallelogram, this one here. So this one all the way down here like this, and like this, and like this. Now why do I want to do that? Because now we won't actually have to paste this over, but the way they would do this in a geometry class, right, is they would snip this piece over here like this. They would put it over here like this, right? And then we can see that the area of the parallelogram is just going to be the base times the height, like that. In other words, the area of the base, there's B, right, times the height. And there's the height. Now the height, by the way, is really easy, right? That's just 7. The base is going to cause us some problems. Now what do we want? I'm going to try to find the x-coordinate right there of that point, x0. And I'm going to use the picture that says that this vector plus this vector equals this vector. I'm going to write that down here and I'm going to solve it up there. So I want the vector x0 plus this little vector over here. Well, what do I know about that little vector? Not a whole lot, except This little vector here is parallel to the vector 3, 7. And being parallel means it's a multiple of, so I'm going to write some multiple of 3, 7 equals the vector that starts here and ends here, that's 5, 2. Like that. So in order to find x, I actually have to solve this system of equations. Let's go look at that system of equations. We'll probably have to recreate this picture in just a bit. But meanwhile, I have a system of equations I can look at. And we're going to use every definition we actually saw. Right? So I'm going to write down x, 0, plus lambda times 3, 7 equals 5, 2. Now what does it mean to scalar multiply a vector? You just multiply each component, so this is the same thing as saying x, 0 plus 3 lambda 7 lambda equals 5, 2, like that. What does it mean to add two vectors? We add their components, so this is x plus 3 lambda. This is 0 plus 7 lambda equals 5, 2. What does it mean for two vectors to be equal? It means their components are equal. And finally, we can write down the equations we need. So equation 1 would be x plus 3 lambda equals 5, and 0 plus 7 lambda equals 2. We can solve this any way we want to. I think treating this like a system of equations from linear algebra is probably overkill. I'm just going to solve the first one for lambda. I'm going to get lambda equals 2/7. I'm going to plug that back into equation 1. And I'm going to get x plus 3 times 2/7 equals 5. So that x is equal to, what do I want here? I want 3 times 2 over, oh, no, not, sorry. I have to throw it on the other side. I'm going to get 5 minus 3 times 2 over 7, like that. So that's finally x. All right, I'm going to go back to our original picture and reinterpret everything. Remember, our picture looked like this, right? Where we had, this went over to 5, 2. This went up to 3, 7. Like this, our original parallelogram looked like that. We are finding the area of the parallelogram we get by snipping off that and putting it down here. We know that this height is the same as the height of this point, so we had written down h equals 7 over here. We just found that this value right here, and let's see, that's deciding not to write for me. This x value right here, so this is the length, it's going to be the length of the base, right, is 5, come on, 5 minus 3 times 2 over 7, like that. And so the area of the parallelogram we're looking for, right, which is equal to the base times the height. The base was 5 minus 3 times 2 over 7. The height is 7. We just distribute the 7, and we're going to get 5 times 7 minus 3 times 2 is going to be the area we're looking for. Now, let's go back to the very beginning of the problem, because the idea was we were starting with a matrix whose columns were 5, 2, and 3, 7. And we find that the area of the parallelogram formed by the columns is equal to 5 times 7 minus 3 times 2. That should look very familiar to you from your linear algebra class, right? This is actually what's normally written down as a determinant of that matrix. But we can see by trying to find the area that we come up with the determinant. That's very different than saying, here's a formula for the determinant, what is it good for? All right, now in the next activity, I ask you to do the same thing, except with an A, B, C, D there. So the same picture applies, but you get to run through everything. Every bit of that argument we're going to be using in lots of different places, so recreating that's really important.